Okay, so let's go back to our introductory slide. Talking about my publication of the book. So in the sixth semester, I offer a course on cellular communication, and I use this book as the main textbook in that course. Now, this course will present one of the two types of telecommunication. And you know that communication means the transfer of information. And the information can have many different types. The two types, are wired and wireless. You can use either they wire, I mean the transmitting and receiver side can be connected via a wire, and that's the wired communication. The other type is that we don't use any wire, but we still transfer the information. So that's then that can, I mean, I oftentimes call it weird communication. Okay, the first step is wired, and this step is weird. We don't use anything to connect. So, but it still works, and so that's wireless communication. So we'll be covering the second part. However, we will try to have an overall idea of the wireless communication, and so that will sometimes incorporate some idea about the wired communication too, just to have a better idea about, I mean, holistic idea. We will have to talk about, for example, sometimes we have to compare this, or we have to discuss the, I mean, wireless communication, comparing it to its counterpart. Okay. What benefits or the challenges are there we have in wireless communication. So when you compare it with the counterpart, then you have a better idea of this option. If you have two different options, you may have to even select one of the two, which may better suit to your particular case. So we have to say a little bit about the first step, on and off. Now, for wireless communication, the signal that you use for the transfer of information, the transmitter will send a signal, the receiver will catch. And this signal can have a range of 3 kilohertz to all the way 300 gigahertz. However, practically it is up to 100 gigahertz. Okay. So theoretically, it is 3 kilohertz to 300 kilohertz. And the wireless term has a synonym like radio. So these are also called radio frequencies, or RF. So RF frequencies, RF or radio frequencies, mean a range of 3 kilohertz to 300 gigahertz. I didn't write it here, but you may note down that the RF, when you say RF, it means radio frequencies. It actually means a range of frequencies from 3 kilohertz all the way to 300 gigahertz. But just keep in mind that the practical frequencies are not higher than 100 gigahertz. They are all in the research lab. Okay. Or in some delicate cases, not in commercial use. And mostly it is the frequencies also lie within several tens of gigahertz. If we talk about most of our cellular commercial cellular deployments, then it's within uh, 3, 4, or 5 gigahertz, not even higher than 5 gigahertz. The cellular communication, not even higher than 3 gigahertz. Some Wi-Fi applications use up to 5 gigahertz. But as you increase the frequency, you have higher challenge. So the frequencies are usually on the lower end. As the textbook, we are referring to this book as of now, Wireless Communications, Wisdom Practiced by Rappaport. It's one of the most popular books, but you know what? We'll try to have a good overall idea. So we'll have to touch upon many different things, and these things are not well covered in any single book or in any single source. So there will be in most cases you'll have to rely on the lecture notes and my discussion. Okay. I'm sorry, but we cannot use one or two books as the good reference for the whole course. The lecture materials and books will be shared in Google Drive. And throughout the whole course, please try to make it interactive. Whenever you have any questions, don't hesitate, don't feel shy. Just thinking that what others might be thinking about you. If you have something unclear, just raise it in the class. Okay? That may really help others. There may be other people also who are not understanding the same thing. I don't guarantee that I'll be able to answer each and every question, but if I fail, then I just further check on it and come back with the answer on the next day. Here's my contact information. You can contact me anytime. Again, I don't guarantee that I will answer. I'll be picking up your call. Okay. A lot of times I miss the call, but you can try to reach me anytime, whenever you need. Okay, it doesn't have to be our regular office period or daytime or whatever. If you need any assistance, you can contact me anytime. If I miss your call, I'll call you back. The same number I also use for WhatsApp. Okay. Now, that's all the introductory speech from my end. Let me hear from you guys. Well, what do you think about this course? First of all, let me know why you have, it's an optional course. For the first time in this semester, you have the option to select some courses. So let me ask you why you have selected this course. You are then absent-minded, or while you are selecting, what is the reason? By mistake you have chosen this course, or how have you ended up with selecting this course or coming up here in this class?
No, sir, we didn't mistakenly ended up.
Sir, did we do a mistake, sir?
No.
No, that's my query.
Sir, we don't know,
We
sir.
will
Sir,
see.
we took it, sir, because, sir, it was given to us, sir. Like, we read the stuffs that were given in that outline. Little
And
outline.
those stuffs
Anybody
look
gave it to you?
Yes, sir.
Anybody gave it to you? You opted
No,
for it.
no, no,
Right?
sir. It's our conscious decision, sir.
Oh, really?
But sir, now you're asking us that question. It's making us reconsider.
Okay. Uh,
Yes, sir.
then, if it is not by chance or by mistake, then what is the reason?
Actually, the course outline, the topics that were supposed to cover seemed interesting.
Yes, sir. Seemed interesting.
Yes.
Uh, Good.
Yes,
To me also, you know what? I myself don't find, don't feel good studying anything. Okay. I feel, I feel like sleeping all day. But the reason I came to this area, okay, that it is, say I first selected electrical engineering because it is the least boring thing. I mean, all different areas, electrical engineering is the least boring thing. And then again, within electrical engineering, telecommunication is the least boring thing. And then again, wireless communication, the least boring thing, and the cellular communication, the least boring thing.
So,
Okay.
sir, you're telling that it still is boring, but least among the other.
Yeah. I mean, to me, everything is boring. Okay,
yes, sir.
except sleeping all day.
Yes,
But I just had to go for the least boring option. Something I have to choose for my life, right?
yes,
Okay. So, but if you want to put it in other words, then you can call it. I mean, it is more interesting than everything else, than all other areas. So, well, and I think most of you will have the same feelings as I have. Okay, after we complete this course, you'll feel that this area is more interesting than everything else. All other fields uh, will be will be more will be less interesting. And also, cellular communication is an interesting aspect within wireless communication. So I think most of you will have the same type of feelings, uh, and we will try to have, as you said, that we will try to have a uh, overall idea or holistic idea instead of uh, focusing on uh, going covering something in very good detail. We will try to have a good idea uh, of of the whole technique, okay? And we will have that will help to have a clear uh, or you'll feel comfortable, okay, with otherwise people are sometimes okay, I mean they know many things very well, but they don't feel comfortable with the whole wireless communication stuff. People don't feel comfortable. But well, we'll have we'll be covering many different aspects to make you feel comfortable. And although we won't be able to manage time to go to cover something from a very good depth, okay? But whatever depth we can cover will probably give you a clear idea. And if it is not clear, you'll always be allowed to ask me questions. So, until it is clear enough, we'll be talking about it. Inshallah. If needed, we'll go deeper. Okay. If you have more queries, we'll go deeper. Okay. But my plan is to cover uh, more number of things. Okay, so you feel more comfortable. This is, I think, just the beginning of your journey in communication area. So if you feel comfortable from the beginning, Okay, then you can go far. Okay, and I need to track your attendance precisely, because from this year we have some obligations at the university to keep record of everything. We'll go for the university, we'll go for some accreditation, and you have to document different things, and you have to formally submit them for the accreditation process. So I actually need to track your attendance today. I need to know how many of you are here today from section A, from section B, and from section C. Okay, so here I'll be okay, just give me a second. Well, but meanwhile, please tell me what you are thinking about this course, or what you feel. Okay, let's
I
ask
feel
you some. Yeah, go ahead.
optimistic, sir.
Yeah,
I'm feeling optimistic, sir, today, early in the morning.
okay,
Yes, sir.
optimistic.
And sir, we are very new. We don't have much idea,
Right.
sir? So we are very new. So we are here to learn, sir. That is it.
Yeah, optimistic means you are expecting more than what is going to happen in reality.
Absolutely, sir.
Okay.
Yes, sir.
And
We're ready for disappointment, sir. Yes, no
yeah,
problem.
okay, but I think I mean, my impression is that you are pessimistic. You'll be getting more than what you are expecting.
Alhamdulillah, sir. Then that is really good, sir. That is good, sir.
So, well, but you, but as we go far, I mean, as we proceed, okay, you since we are covering many different things, and once we aggregate, okay, you'll have more holistic ideas. So your concept will be developing throughout the course. So as we approach the end, or as we go towards the end, you'll have better and better idea. So until you complete the whole course, I think you don't have a good impression about what we are going to really deliver here. Okay. So I'm telling this to you because on this first day, maybe it is better to raise this issue. It's because the cellular communication course is is a subset of wireless communication. I mean, wireless communication includes all different types of communication that you use when you have the transmitter and the receiver, okay, uh, connected without any wire. So cellular communication is just an example of wireless communication. So it's a subset of wireless communication. So after you complete this wireless communication course, most students uh, prefer taking the cellular communication course. That is also an optional course. Most students want to take that course. But when we are halfway through this course, they don't have enough impression. So many students uh, have, choose some, think that other course may be a better option for them for the sixth semester. And the authority collects the choice in the middle of this course, middle of this semester. not at the end. So at the middle, or when you are halfway through the course, many students, that's happening every year. Many students, they think that, well, the other, I don't know what the counterpart is for cellular communication, but many students choose the other subject. But when you complete the course, these students have a strong feeling that they should take cellular communication. But the present authority doesn't allow this change of option. And they become crazy. These students become crazy. They just start fighting. That's happening in the, since we started this cellular communication course, it is happening every year. Many students at the end of the course start fighting with the authority. The authority doesn't want to allow any change. They just go crazy. They anyway, desperately they want to take the course. So if you, if you have, you may just, first of all, you may want to wait until the last day for giving the option. Okay? Or you may try to have a better idea what you might going to have in this course. Okay? But from my end, I'm also helpless because I have to cover a few things early and few things later. So I have to proceed in a particular way. So you'll get a good idea. We cannot get a good idea until we get to the end. Anyway, let me ask you something. Let me test you with a question. You know that people sometimes do modulation of the information signal before transmission. The transmitter in the communication setup, we transmit the information in the form of signal from the receiving end, we catch it. Now, before the transmission, the original information may be modulated. So, can you tell me what the purpose of modulation is? Why do you do the modulation? What if you directly transmitted the information? Yeah, please. Go ahead.
Can I answer, sir?
Yeah, sure.
Sir, it is because the normal voice or the information that we intend to send, if we are to send that data, that would need a huge antenna. And to reduce that antenna size, we use modulation so that we can increase the frequency and then significantly reduce the antenna size.
Okay. That's the correct answer. Thank you very much.
Welcome, sir.
There is a second reason. So there are basically two reasons. So it's one of them. Can anyone tell me the second reason? Both reasons are equally important. Can you give me the second reason? Consider practical cases.
Sir, I slightly got disconnected. Can you?
Yeah, I was asking why people do modulation before transmission, and there are two reasons for the modulation.
Encryption.
Yeah.
Sorry.
Yeah. Go ahead, Fatin. Yeah.
Encryption. So, sir, it cannot be directly received by someone else.
No,
that's not the main reason. If it's
send multiple
separate
information
signals.
together, sir. Send multiple signals together at the same time without interference between them or interaction between them.
Yeah. That's the other reason. Thank you very much. So you well, so I mean, first of all, from your answers, probably it is getting clear that you need modulation when you use wireless communication. I mean, in general, you need it in the case of wireless communication. Because the first answer was the use of antenna. And you use antenna for wireless purpose. For wireless communication, you have a transmitting antenna and a receiving antenna. And that antenna dimension will go down as you increase the frequency. So using modulation, you raise the frequency and reduce the antenna size. So that's one reason. So you do modulation for wireless. Secondly, in the air, many people will be transmitting their information. Okay, so the air is open for everybody. So all people have information, and the original information frequency range is pretty much the same for everybody, whether it is voice or video or text or whatever. So if all start transmitting together, then they all will be interfering with each other. So using modulation, you put them at different frequencies. Modulation is just translating the frequency. And so you change the frequency to a higher level, and that new level will be different for different people who are using the same airspace. So that's how our, say, FM radio channels or say TV channels. Okay. So they are many channels are coexisting, and they are transmitting at different frequencies. So they are all modulating at different frequencies. Very good. The reason I ask this question is that there is a myth. Some people think that we need the modulation because we need to send the signal far. And to send the signal far, higher frequencies are required. If we use low frequencies, the original information is usually at the lower range. So if you use these low frequencies for transmission, the signal will shortly die out. It cannot go far. So we need to increase the frequencies, and then the signal can go far. Sometimes people also give an example that if you use some small thing, then that can throw it. It doesn't go far. But if you take a large thing and then throw, then it can go far. Okay. Well, it's all myths. Okay. Even the example is myth. Okay, try throwing small and large things. Okay. The small thing will go further. Okay. And also, as you raise the frequencies, the signal dies out at a shorter distance. Okay. The signal dies out at a shorter distance when you increase the frequency. So it is the other way around.
But
The
sir,
lower frequencies are good for covering larger area. Yes, go ahead, please.
I mean, from common sense, actually, what I think actually the signals with higher frequencies holding much more power, and the lower frequencies holding lesser power. So why actually the higher frequencies dies out faster than the lower frequencies? I mean, it's quite contradictory with my, natural sense. Can you explain actually why the higher frequency dies out faster?
Sure. Well, see, let's go back to your first course with electrical engineering. So when you calculated power, how did you do that? say from voltage or currents, you calculated power.
Yes.
You had say instantaneous equations,
Yes, sir.
and say V sine omega t plus theta, I sine omega t plus theta. Okay, so you had this type of expressions for voltage and currents. And when you calculated the power, how did you do that?
I multiplied the voltage with the current.
Right. Okay. Okay. So you had there the amplitude,
Yes, sir.
the frequencies or omega,
Yeah.
and theta, right? You had
Yes.
actually 3 variables. Okay.
Yes.
So when you calculated the power, did it depend on frequency? Did it?
No, sir. Actually, that
It
was.
didn't. It didn't.
No,
So that's the myth. That's the myth. People think that higher frequency signals are holding more power. That's not the case.
Okay, I got it.
It all depends on the amplitude.
It depends on that.
And the relative phase difference is sort of vague for us because that
Yes.
depends on many different factors in the environment. So you mostly think about the amplitude level.
Yes.
So in this case, in wireless communication, you send the signal, and you need to consider the electric field and magnetic field. Uh, the electromagnetic wave is comprised of these two fields. So the amplitudes of these two fields will dictate what the power content you have in the wave. The wave is definitely carrying power. It depends on the amplitudes of your fields, not the frequency. First of all. Secondly, that might you might argue now, well, then the power content is the same for all frequencies. So the signal should cover the same distance at all frequencies. Why do you say that a high frequency signal will cover a shorter path? I said that it is the other way around. It is opposite to visual understanding. If you ask electrical engineers who did not graduate from IUT, okay? I'm not talking about mechanical or civil engineers. I'm talking about electrical engineers, but who did not graduate from IUT, okay? Graduate from some other universities of our country, important. You ask them this question, okay? In which case the signal will go further, whether it's lower frequency or higher frequency. You'll find that he's answering wrong. Okay. So people think the way you were. So okay. So first of all, we have the same power content, but then it comes why it goes it dies out at a shorter distance as you increase the frequency. Well, there are multiple reasons, but today to give you a very quick idea, I can tell you that as you increase the frequency, the wavelength gets shorter. Probably you in some physics course or somewhere you found C equals to F lambda or V equals to F lambda. This sort of expressions you found before, right?
Yes, sir.
Yes, sir.
F and lambda, okay? Frequency and lambda are inversely proportional to each other. So as you increase the frequency, your wavelength gets shorter. And the signal, okay, from the viewpoint of the signal, you have a shorter distance for every cycle. Every cycle finds a shorter path, shorter physical distance, because your wavelength is getting shorter. So that, I mean, the coverage will be shorter. And the most important factor here works this way actually. I mean, you have the same loss of power. The signal, of course, gets weaker as it propagates. But this attenuation occurs in terms of wavelength, as we'll be showing using equations in this course. But that's the most important impact that you, I mean, attenuates this way, that in terms of the number of wavelengths, you have an attenuation. So if you have, say, 100 cycles, 100 wavelengths covered, then you have the same percentage of attenuation. Now, if the wavelengths are larger, then this 100 wavelengths will cover a larger distance, and the lower frequencies will cover a larger distance. Okay. Got it?
So isn't it then a little counterintuitive? So isn't it like at the end of the day, the higher frequencies are going a smaller distance because attenuation is more?
Yeah. As you have higher frequencies, the signal will be weaker at a shorter distance.
Weaker at a shorter distance, but
I mean, we'll have the same power level at the same weakness at a shorter distance.
okay.
Lower frequency is when you transmit with the same transmit power.
Yes.
Lower frequency signal will have a particular signal strength at a larger distance. The same signal strength will be at a shorter distance for higher frequencies.
Okay. So higher. Isn't it like that? If we compare the higher and lower frequencies together, the higher frequencies are not covering a larger distance.
Right.
But so you said it is covering a large distance.
No. I said that with high frequencies, you cover a shorter distance.
Okay.
Sir, for waves, sir, most probably the expression of power was both proportional to amplitude square and frequency square.
It's not.
So maybe, sir, the expression was like half mu amplitude square omega square into some constant.
It depends on power. I mean, what you are saying is correct. When you have the signal in some guided way,
Yes, sir.
the signal can be either launched and you let it propagate free. That's what you do with antennas.
Sorry, sir, I
The
couldn't.
open space, you launch the signal and let it propagate free. The other option is that you use some guide in the circuit, okay, for high frequencies. I mean, we'll discuss later that you may have to launch a signal and guide it through your circuit for testing. In that case, it is a guided wave. And the calculations are very complex for guided waves. For guided waves, it's correct that the power level depends on the frequency too. The equation that you have also is more complex, and that includes frequency term. But when you have free signal, then free space signal is independent of the frequency. I mean, its power content is independent of the frequency. It just depends on the function of your amplitude. Well, the relative direction of electric magnetic fields is a factor. The phase difference is a factor. But those things we can ignore for ordinary cases. I'll tell you why later. So, I mean, to In ordinary cases, we need to consider only the amplitude. Although in the equations you have the angles too, but not the frequency. You don't have the frequency at all in the power expression. I mean, just like you're pretty much like what you had in the electrical engineering course. When you calculated power, you didn't have frequency term, but you just didn't notice it. I mean, probably most of you had the impression that high frequency, even for electrical signals, you had the impression that high frequency signals have higher power content. That's not the case.
The conclusion from this discussion here is that larger transmission frequencies can only transmit for a smaller distance, and the lower transmission frequencies
Yeah.
are used for higher distance transmission.
Sir, is
In
that
fact,
for
mean-
like 5 gigahertz band in routers? We cannot use it at a long distance, right? But suppose
yeah, I mean,
gigahertz,
the Wi-Fi routers use either 5 gigahertz range or 2.4 gigahertz range. 2.4 frequencies will be covering larger area
yes, sir.
compared to 5. Okay, now actually, you know what? I had our first lecture ready. I mean, I wanted to discuss it today. That was about wired communication. The reason is that we have to have a good idea of how, I mean, idea about selection. Okay, when you should go for wired, when you should go for wireless. So one lecture I will be using for wired connection. Actually, what type of wires you have, that I will just discuss in this lecture. I wanted to cover that today, but I was just talking different things. And I didn't happen to start discussing that. So from the next class, inshallah. Now we have 20 more minutes. Okay. So, but a couple of things we need to settle. We need to just mention here. First of all, Inan collecting your email addresses. I need a whole list of email addresses. So I can create a Google Classroom for you. We'll be using Google Classroom for our notices and announcements and for tests, all kind of tests, class test or midterm final or assignments. For all of them, we'll be using Google Classroom. And the lecture materials, all lectures will be available in PDF, and also our recorded video lectures. They all will be shared in a Google Drive folder. So once we get your email addresses.
Okay, sir, I
Yeah,
will
Ina?
be providing you by tonight, inshallah.
Okay, thank
Sir,
you.
I am taking
very
the
much.
response.
Okay, thank you very much. So I'm just telling everyone because you guys helped Inan. And secondly, it's an obligation this year for us to track your attendance beside every class. So I have to find out you know what? I don't feel like calling everybody in the beginning. I feel like an elementary school. But I need to find out a good way to do that. Actually, there's a list of participants I can see here. And I think that will be there even after the class. Hopefully.
Sir, BDRAN gives you a list of the participants after the meeting.
So, what do you say? I mean, you can give me. You're saying that?
Sir, I am saying that since you are using an BDRAN account,
Yeah, yeah,
you will get that participants
Right,
list after the
right.
meeting.
right. That's what I was also thinking about. I wasn't sure of it. Uh, okay, but hopefully it will be there. Okay, so then I'm not calling the same numbers. Just collect the list from there. Okay, since we have another 15 minutes, I think we can begin the presentation. Right? If you have any questions, please go ahead.
No, sir.
Okay, so the wired communication can use different types of wires or cables. And let's see what they are. There are four major types: twisted pair cable, coaxial cable, or in short, coax, optical fiber, and waveguides. So these are used for communication purpose. Okay. For power lines, ordinarily power transfer, you know what kind of wires you use. Right? So for communication purpose, you use different types. Why you need a different type? Okay, that will also be little clear. We won't spend much time on it, but I mean, if you ask me questions, I'll be answering your question then, and so I'll take more time. But the first type, twisted pair cable, uses a pair of insulated wires twisted together. Oh, sorry, I wanted to include a figure here, but I forgot that. Okay, let me show you a figure from here. Okay, you see that these cables are twisted. Okay, actually, I wanted to include another figure, really showing more twisting. Anyway, here also we can see that there are there are four pairs, but each pair is twisted on its way. So it's a twisted pair. The whole cable can have multiple pairs. Okay? And in different cases, you have seen the old uh, telephone cables. Probably you haven't seen them. In my boyhood, I saw actually some twisted pair cables for the telephones. So anyway, these twisted pair cables have two categories: unshielded and shielded. So then they are called UTP or STP. The first type, UTP, is widely used, and the Ethernet cables that we have, all of you are familiar with, are mostly the UTP type of cables, what we call in general Ethernet cables, because the protocol that you use when you connect using these cables is Ethernet. So people started calling the cables so Ethernet cables. So the actual name of the cable is UTP. The protocol means how the computers will be communicating with each other. So you need a protocol there. So that protocol is specified by IEEE. The specification number is IEEE 822.3. This 822.3 protocol has the name Ethernet. Anyway, you may be curious why you need the twisting. Well, it's to help that your cable is more robust from the interference. I mean, you have less impact from the interference of external sources. There will be some electromagnetic fields from outside, and that can induce some currents. You may have some magnetic field around, and that can induce current in your signal, in your wire. So there can be interference in your wire. But if you have twisting, then you can reduce this interference. This interference can also come from some other pairs in the same cable. As we showed a while ago, 4 pairs were there, and that's actually a common example. In Ethernet cables have 4 pairs inside. So if you have 4 pairs inside the cable, within your cable itself, then these pairs, one pair can interfere another pair. And if you have that, then it is called crosstalk. The crosstalk, as you can see that crosstalk interference comes from other pairs within a cable. Within the same cable, when one pair interferes another pair, then it is called crosstalk. And when you have interference from another cable, because every current carrying conductor has fields around. There is magnetic field around current, right? Also, a voltage difference means you have some electric field. So anyway, the fields of one cable can induce another cable or interfere another cable. So you can have some changes in the current in another cable, and that is called interference. Now, let me show you how the twisting helps. For example, some field is coming this way. This from external source. Some fields are coming this way, and because of this field effect, the closer one, now we have straight wires. We haven't twisted. So 2 wires we have, and there is no twisting. So the upper cable is closer to the source of the interference, to the source of the electromagnetic waves. Source of the electromagnetic wave. So the upper cable gets some higher voltages induced. So see, on every segment, we have 1 millivolts induced because of this interference. Because of this interference arriving, we have 1 millivolts induced here, 1 millivolts induced here, 1 millivolts induced here. So in total, on the upper cable, we have 6 millivolts induced between the left and the right corners. Okay. Now, in the lower cable, okay, in reality, things don't work exactly the same way, but it's a good way to explain. In the lower cable, which is further away from that source, you have lower voltages induced. So you have 0.5 millivolts induced in every segment. So between the left and the right corner, you have 3 millivolts induced. Now, if you compare the voltage difference here, which is most important, okay, how much voltage difference you have induced between your wires. Okay? That is just the actually important thing. And you have a 3 millivolts difference induced, because you had here 3 and for lower one, and for the upper one it was 6. So between upper and lower one, you have 3 millivolts difference. Okay. Now, if you can you follow me? Can you guys follow?
Yes,
Yes,
sir.
yes.
Okay.
So
Now,
one more thing.
if I twist, yeah.
Just to be clear, actually, the interference you're actually talking about changing magnetic field, which actually cuts the wire and induces voltage. Is that something so?
Well, for now, you think about electric field.
Okay.
Okay. I mean, both electric and magnetic fields can induce. Okay. For now, think about electric fields.
Okay. Sir.
And these are, I say, just crude examples. Okay, just for the purpose of explanation. Now, if we twist, then you see the closer one is not fixed. You're twisting. So the red one, the blue one is getting 1 millivolts here, and then the blue one is getting 0.5 millivolts. Again 1 millivolts, 0.5 millivolts. Okay, 1 millivolts, 0.5 millivolts. So the blue one is getting 4.5 millivolts between the two corners, left and right corner. The same will be the voltage difference for the red one, 0.51, 0.51, 0.51, 4.5. So between the two sides, we have no voltage difference. So you don't feel that there is an interference from outside. If between your two sides, no voltage difference is created from the external fields. Okay, so you can see that because I mean, with twisting, you change the location. So it will be closer or further from other source, but you change the position. Okay. So you alternate the positions of the two cables, and so they are equally affected. So you see that the twists reverse the polarity of the conductors at each and every twist, and this cancels out the difference in the individual electromagnetic fields. So the difference is cancelled out. Another thing, we won't spend much time on it, but anyway, you may just encounter when you look into the cables, okay, the Ethernet cables. There are some devices to cut and to connect RJ45 for Ethernet cables. You may have to do that sometimes. So you'll find that different wires have different twist rates, with different pairs have different twist rates. So let me just give you the reason. But anyway, let's we'll try to go faster. Different twisters are, some pairs will have more twists per inches compared to others. This is because this is to reduce crosstalk. Okay. Each of them are generating some fields. So when you create some harmony, okay, then there is more chances of crosstalk. If they have different rates, then you avoid an harmony. Use different rates. Then the crosstalk, okay, the impact from one on the other will be reduced. When you have, because the the interference coming from outside, okay, is not what you are using for your own twist tapes. I mean, they are not coming in the same way. So you can find it, say, in our example, the interference was coming in an uniform way compared to our twist. So, but
Yes.
if you also have the same kind of changes on the source end, then the interference can also have, I mean, you have different segments. Okay. The interference will also have different segments. I mean, will also be having differences in the, you are canceling out the differences. Let's go back to, we're running out of time. All the interferences are the same here, but the differences are cancelled out because of twisting. But if you have differences also at the different segments at the interference, then again you may end up with some difference at the end. At different segments, if you have different type of interferences, if they also come with the same type of segments, the interferences have also variation at the same segment breadths, at the same levels of segments, then you can end up with some difference at the end. So that's why you use different twist plates for different pairs.
Sir,
The shielding, there will be shielding around, even for UTP, you have something around. So that can help a lot for the interference coming from external sources. But the crosstalk is important. Yeah, go ahead.
sir, we have another class.
Oh, yeah. Yeah, so let us stop here. Thank you for your time. Jazakallah. I'll see you tomorrow.
Assalamu alaikum.
Waalaikum salam.
Assalamu alaikum.
Waalaikum salam.